What we're going to do is we're going to look at determining the pH of weak acids and weak bases. We're going to look at what the concept of ionized partially means. Now we know a strong acid ionizes completely. This means that the concentration of the hydronium ion or proton will be equal to the concentration of the acid, because everything that every acid particle I have become a proton or hydronium ion. Whereas in a weak acid, because they ionize partially, this means that they set up a dynamic equilibrium. And this dynamic equilibrium means that not all of the acid ionizes. Right? Some of this will ionize to that, but I keep different amounts of my acid not ionized. So as a result, my concentration of my acid is always greater than the concentration of my ion concentration. So we need to have a way to get our ion concentration. Since they establish a dynamic equilibrium, that means that they have an equilibrium constant, and we can use all the strategies that we've developed for determining the concentration of the proton. But for an acid, we call our equilibrium constant an ionization constant, and we label it a Ka because it's ionizing. Okay, and we can write our Ka expression, or equilibrium expression, with either a hydronium or a proton ion, because the inclusion of water does not affect the expression, because water is in liquid form, therefore it has a constant concentration and it's not included in the expression. Okay, so we call our Ka our equilibrium constant and not ionization constant. Similarly, we can have the same thing occur with weak bases, because weak bases will ionize partially. And so if we use the generic symbol B for our bases, they will act as the Bronsted-Lowry proton acceptor and results in the formation of hydroxide. And when we write our Kb expression, we have this. Okay, and we call our Kb an ionization constant. A couple other things we want to look at first: polyprotic acids. Polyprotic acids are acids that can ionize and produce more than one acidic proton. The key is they release one proton at a time. Okay, so here's our phosphoric acid, sulfuric acid are examples of polyprotic acids. Sulfuric acid, the ionization for the first proton is strong, but the second is weak. But each one comes off independently. So if I had a polyprotic acid that had 3 acidic protons, and I know it has 3 acidic protons because I have the subscript here 3, and it's at the front. Each one comes off. So first I'll have my first acidic proton come off, then my second acidic proton will come off, and then finally the third acidic proton will come off. Because each of these are independent equilibrium equations, they all have their own equilibrium constant or ionization constant, and they would all have their own equilibrium expression. Okay. Like polyprotic acids, we can have polyprotic bases where they accept more than one acidic proton. Okay, and each acidic proton is accepted independently. So we would have an expression where we accept our first acidic proton, and then we accept our second acidic proton. And because these are separate equations, again, they would each have their own ionization constant. Now, let's go back to the autoionization of water. This is actually a dynamic equilibrium that sets up where if I had a sample of pure water, some of the water would ionize to produce hydronium and hydroxide ions. And we know this intuitively because in a sample of pure water, it has a pH of 7, which means that my concentration of my hydronium ion is 1 times 10 to the negative 7, and the concentration of my hydroxide ion is 1 times 10 to the negative 7. So 1 times 10 to the negative 7 times 1 times 10 to the negative 7 gives me 1 times 10 to the negative 14. So let's take a little mathematical aside. Don't worry about copying this. This is just so you can understand where a relationship that we've been using since last year came from. And we're going to use this relationship again. So our Kw is equal to concentration of hydronium times hydroxide. So let's take the log of both sides. Then we'll apply one of our log rules. Then we'll multiply both sides by -1. And we know this value is 1 times 10 to the negative 14. We can call that pKw plus pH plus pOH. And we know this value, which becomes 14. So 14 is equal to pH plus pOH. Now, when an acid ionizes, we have our acetic acid here, it undergoes this ionization reaction. It produces a conjugate base. This conjugate base can be a proton acceptor. So if I added sodium hydroxide to solution, the conjugate base could be a proton acceptor with water being a proton donor, and I produce that. So the question is, what's the relationship between the Ka value for my weak acid and the Kb value for its anion, which is a conjugate base? Well, I can write my expression for my Kaw, my Ka value, and I can write my expression for my Kb value. Now, the way these equations are, that doesn't help me to understand the relationship, but if I manipulate them and I isolate the one variable, concentration of my hydronium ion, and likewise I'm going to do concentration of hydroxide. Now I'm going to take these, I know these two values have a relationship, Kw. So if I take these two, substitute this in now for my hydronium ion concentration, and this for my hydroxide, I can cancel. I get the Kw is equal to Ka times Kb. So the ionization constant for a weak acid times the ionization constant for its conjugate base is equal to Kw. This relationship will become very important. Okay. Likewise, the ionization constant for a weak base times the ionization constant for its conjugate acid is equal to Kw. So let's look at a couple of examples. Now in this example, we're told the pH of a weak acid solution, and we're asked to calculate our ionization constant. Just because we're dealing with acids and bases and their ionization constants doesn't mean that we throw everything we know out. First we write our equation, and because we're not told the formula for the weak acid, we'll use Ha, because we know that it has at least one acidic proton and it'll produce an anion when it ionizes. And we need an ice table. We're told our initial concentration of our acid. We know that our initial concentration of our anion before the acid ionizes is 0, but in this case my concentration of my proton is not 0, because in pure water we have some proton or hydronium ion due to the autoionization of water. And so we start off with 1 times 10 to the negative 7. Now we're going to put it in brackets because we're recognizing that it's there, but it's not going to be significant at my equilibrium. Okay, and so some of my acid will ionize to produce my protons and anions, and so I have my equilibrium concentrations. Then we need our equilibrium expression. Okay, and now in this case I don't know either my X value or my Ka. However, I do know my pH. Okay, and we know that my proton concentration is equal to 10 to the negative pH. Okay, and with weak acids, it would be my equilibrium concentration. So I can substitute that in, and I get my equilibrium concentration of my proton, which tells me my value of X. Okay, so I can substitute it in to determine the equilibrium concentrations of my other two entities. And now that I know my equilibrium concentration of everything, I can substitute it into my equilibrium expression and calculate the value of my ionization constant. Okay, so let's look at an example where we're asked for our pH. Okay, we need our equilibrium expression, again our ionization. We're going to use HA once again for our acid. Our ice table, we have our initial concentration, our change, our equilibrium. We do our equilibrium expression. Okay. Now before we go off and solve, we can see that our Ka value is really small. Okay. And so I'm going to therefore do my check. And I can see that that's greater than 500. So I'm going to use method of approximation. And this suggests that not a lot of the acid will ionize. So then I solve. And now because I made the assumption, I have to do proof. I see that's less than 5%. So it's a valid assumption. So now we know our concentration of our protons. And we can calculate our pH. Hey, what about if it was a weak base? What would the difference be? Nothing. We need to first get our balanced chemical equation, then our ice chart. Okay. And in this case, before it ionizes, my concentration of my cation formed in the ionization reaction is 0. But my concentration of hydroxide is not, because it's pure water, so it's 1 times 10 to the negative 7. So some of this will ionize. Okay. We write our equilibrium expression. Because of my values, I'm going to do a quick check. It's greater than 500. So I'm going to use my method of approximation. I get my X value. Now I'm going to do my proof. And it's less than 5%. So I know my concentration of my hydroxide. So now I can calculate my pH in one of two ways. I can use the relationship of Kw is equal to the concentration of proton times hydroxide, and I get my pH. And this exists no matter what, because I have two equilibriums here. So this equilibrium, we cause that one to shift. That's why this concentration changes. Okay? Or I can calculate my pOH and then use this relationship. And it doesn't matter which method you use. In both cases, we end up with the same final pH. What about if I had a polyprotic acid and we're asked to determine not only our pH, but our concentration of all of our anions that are in solution? Okay? So we treat each one independently. So first, let's look at our first acidic proton coming off. I would write its balance equation. I would write my ice chart for it. Okay, so I start off 0.1. Again, not. So let's start off with our first Okay, so if I had a polyprotic acid, how would it be different? We would go through the exact same process, except we'd have to do two calculations, one for each equilibrium equation. So we'd have to calculate our first one, and that would give us my initial concentrations for my second reaction. So let's look at our first reaction. For my first acidic proton to come off, I write my ice chart. Okay. Remember, this is not 0 because of the autoionization of water. I write my equilibrium expression. Okay. K value is really small, so I'm going to do my quick check. I'm going to calculate for my value of X. Then I'm going to do a proof. It's less than 5%, so it was a valid assumption. And then I'm going to solve. So now I know my value of X, so it tells me my concentration of my proton, my concentration of my anion. It allows me to get my concentration of my acid. So now I'm going to do the ionization for the second acidic proton to come off. Okay, and so I need my equation, I need my ice chart. This was produced in my first reaction, so that's where my initial concentration comes from. Because my proton was produced in my first reaction, that's where this concentration occurs. And because they were produced the same, their values are the same. Okay? Since I have none of this ion, some of this will ionize. So I write my equilibrium expression. Now this is a really small Ka, so I'm going to do my check. Okay, and when I do my check, because I showed that the loss of X here is not significant, it means that the loss of X here is also not significant. So therefore I can substitute in and I get my value. I'm going to do my proof. And so that tells me my concentration of this anion. Okay. Now that I know the concentration of my proton, I can calculate my pH. So what does this show us? This shows us that with weak acids, depending on the value of the Ka, the first acidic proton will come off, but the second acidic proton does not come off significantly. And often with polyprotic acids, the second or third or fourth acidic proton does not contribute significantly to the pH of the final solution.